Imagine standing on Earth not as it is today, but as it will be long after every city you know has disappeared. The same planet is still here. The same moon is still pulling on the oceans. The same sun is still rising over the horizon. But the future is not a single disaster, and it is not one sudden ending. It is a long sequence of changes, some human, some geological, some cosmic, and each one slowly rewrites what Earth can be. Coastlines move, ice disappears, forests shift, deserts expand, oceans warm, species vanish, continents drift, mountain ranges rise and collapse. The sky itself changes because the star above us does not stay exactly the same forever. And the terrifying part is not only that Earth has a future, it is that the future is already happening. Before we begin, if you enjoy calm journeys through space, time, and the strange future of our planet, take a moment to subscribe to the channel. Like the video if you want more long space documentaries like this. And leave a comment telling us where you are watching from and what time it is right now where you live. It is always strange to remember that people can be watching the same universe from different parts of Earth, under different skies, at different hours of the same rotating world. Tonight, you are watching the Space for Sleep channel, talking about the entire future of Earth in 2 hours. And it's terrifying. And to understand Earth's future, we have to start with something that feels almost too obvious. Earth does not stand still. It never has. The ground beneath us feels permanent because human lives are short. A mountain can seem eternal if you only look at it for a few decades. An ocean can seem fixed if you only measure it from one childhood memory to another. A city can feel ancient even if it has existed for only a tiny fraction of planetary time. But Earth is not a statue. It is a moving system. Its atmosphere changes. Its oceans circulate. Its crust cracks and slides. Its magnetic field shifts. Its orbit is tugged by the moon, the sun, and the other planets. Its climate responds to gases, ice, clouds, volcanoes, living organisms, and sunlight. Even the length of a day is not perfectly fixed, because the moon is slowly stealing rotational energy from Earth and drifting away. To us, Earth is home. To physics, Earth is a process. And the future of Earth is the future of that process continuing. The first part of that future is the one we are already inside. It is not millions of years away. It is not a red giant sun. It is not a supercontinent. It is not an asteroid strike or the final cooling of the planet. It is the changing climate of the world we live on now. For most of human civilization, the climate was stable enough for agriculture, cities, trade routes, coastlines, and nations to form around familiar patterns. Rivers flooded at certain times. Monsoons arrived with a rhythm. Ice remained locked in mountain glaciers and polar sheets. Sea levels changed slowly enough that many generations could mistake them for permanent boundaries. That stability did not mean the climate was frozen. Earth has always changed. There have been ice ages, warm periods, droughts, volcanic winters, and natural variations in ocean and atmosphere. But the civilization we know grew during a relatively calm interglacial chapter, a window of time in which temperature, rainfall, and sea level stayed within ranges humans could build around. Now that window is being disturbed. Greenhouse gases trap more heat. The oceans absorb enormous amounts of that heat. Ice melts where it once reflected sunlight. Water expands as it warms. Weather patterns shift. Extremes become more likely in some regions. The atmosphere holds more water vapor, which can intensify heavy rainfall in places where storms form. Elsewhere, heat and dryness can sharpen drought. This is not the entire future of Earth, but it is the nearest future. It is the part measured not in astronomical ages, but in policy decisions, engineering projects, migrations, crop failures, adaptation, and memory. If you lived on Earth in the year 2100, the planet would still be recognizable. The continents would not have drifted far enough for a map to look alien. The moon would still rise. The constellations would look almost the same to the naked eye. Most mountains would stand where they stand now. But the human world could feel different in ways that matter deeply. Some coastlines would be more vulnerable to flooding. Some islands would have lost land. Some cities would have built walls, pumps, restored wetlands, or abandoned lower districts. Some glaciers that once fed rivers in summer would be smaller or gone. Coral reefs, already stressed by warming and acidifying oceans, could be greatly reduced in many regions. Agricultural zones could move, not politely, but under pressure. The future does not always arrive like a meteor. Sometimes it arrives as insurance prices, failed harvests, heat warnings, burned forests, flooded streets, and people slowly realizing that the old normal is not coming back. This is one of the most unsettling things about Earth's future. The planet does not have to become unrecognizable to become harder to live on. A few degrees matter. A few inches of sea level matter. A slightly warmer ocean can change storms. A shorter snow season can change rivers. A persistent drought can reshape politics. A heat wave can kill people quietly, not with spectacle, but with air too warm for bodies to cool themselves. The Earth of the near future is not a dead planet. It is a pressured one. And pressure changes behavior. Humans will not simply watch. We will adapt. We will build. We will argue. We will move. Some societies will protect themselves better than others. Some places will gain growing seasons while others lose reliability. Some cold regions may become more accessible. Some hot regions may become harder to inhabit without constant cooling. Technology will improve, but technology does not erase physics. It only changes how much time and energy we spend pushing back against it. That is the first terrifying layer of Earth's future. Not extinction, exposure, the realization that the planet can remain beautiful while becoming less forgiving. And after the near future comes a deeper one, a future beyond living memory, beyond the borders of current nations, beyond the buildings that feel permanent today. 1,000 years from now, almost every political map on Earth will likely be gone or transformed beyond recognition. Languages will have changed. Many of today's cities may still exist in some form, but not necessarily as we know them. Some may become archaeological layers under newer cities. Some may be drowned, abandoned, rebuilt inland, or preserved as ancient monuments from an age that believed it was modern. The climate system will still be responding to what happened before. Carbon dioxide does not vanish from the atmosphere overnight. Some of it is absorbed by oceans and land. Some is processed slowly through geological cycles. But a portion can influence climate for many centuries. Ice sheets, once destabilized, can take long periods to respond fully. Sea level rise can continue even after temperatures stabilize, because oceans and ice do not move at the speed of human regret. In 1,000 years, the question may not be whether humans survived. The question may be, what kind of civilization survived, where it lives, and what it remembers. If humanity becomes wiser, this period could be remembered as the dangerous century when a technological species nearly destabilized its home and then learned to manage its power. If humanity fails badly, the same period could be remembered as the opening wound of a long decline. The planet itself does not care which story we choose. It will respond to energy, chemistry, and time. Earth has hosted catastrophes before. It has seen asteroid impacts, massive volcanic eruptions, oxygen revolutions, ice ages, supercontinents, ocean anoxia, and mass extinctions. Life has been pushed almost to the edge, then changed shape and continued. But humans are different because we can understand the danger while participating in it. We are not only passengers on Earth's systems, we have become a force inside them. That makes the next few centuries unusual in Earth's history. Not because they are the largest changes Earth will ever experience, but because they are changes caused by a species that can see the graphs, read the ice cores, measure the atmosphere, model the oceans, and still decide what to do. But even if humanity solves the nearest crises, Earth's future will not become safe forever. The planet has deeper clocks. One of them is impact. Space is emptier than it looks in movies. But it is not empty. Earth moves through a solar system filled with asteroids, comets, dust, and fragments left over from formation. Most small objects burn in the atmosphere. Some reach the ground as meteorites. A few are large enough to destroy cities. Much rarer objects can alter climate globally. Earth has been hit before. The most famous impact happened about 66 million years ago, when an asteroid roughly 10 kilometers wide struck near what is now the Yucatan Peninsula. The impact helped end the age of non-avian dinosaurs, not simply because of the explosion, but because of the chain reaction afterward. Fire, dust, aerosols, darkness, cooling disrupted food webs, collapsing ecosystems. A future impact of that scale is unlikely in any given century, but over millions of years, unlikely events become part of the background risk. This is one reason Earth's future is not a straight line. You can predict the sun's slow brightening over billions of years with some confidence. You can model plate tectonics in broad patterns. You can describe the long-term carbon cycle. But a single large asteroid can interrupt the script. A supervolcanic eruption can darken skies. A nearby supernova, if close enough, could affect the atmosphere. A gamma-ray burst pointed directly at Earth from a dangerous distance is extremely unlikely. But cosmic history contains events far more energetic than anything human beings have experienced. Earth's future is not one disaster. It is a field of possibilities, with some almost certain, some plausible, and some so rare that they mainly remind us how exposed a planet can be. The good news is that humans can now find many near-Earth objects, track them, and in principle, change the path of a threatening asteroid if we have enough warming. Planetary defense is one of the rare future dangers where intelligence can directly reduce risk. The same sky that once sent surprises can now be scanned. But the sky is only one part of the story. Below our feet, Earth has another future unfolding. The continents are moving. At about the speed fingernails grow, plates slide, collide, separate, and dive back into the mantle. The Atlantic Ocean is widening. The Pacific is ringed by subduction zones. Africa is slowly splitting in the East African Rift. India continues to press into Asia. The Mediterranean is a complicated region of collision and closure. Mountains rise because rock is pushed upward. Then, erosion begins taking them apart. In one human lifetime, this movement is invisible. In 100 million years, it redraws the planet. If humans still exist far in the future, their maps will eventually stop matching ours. The continents we treat as fixed shapes are temporary arrangements. Australia will not stay where it is. Africa will not keep the same relationship with Europe. The Atlantic will not widen forever in the same way, without tectonic consequences elsewhere. Oceans open and close, supercontinents assemble and break apart. Earth has done this before. Columbia, Rodinia, Pannosia, Pangaea. Names given to worlds that existed long before us, when coastlines and climates were arranged in ways no modern human has seen. Pangaea, the most famous, gathered most of Earth's land into a single vast continent before breaking apart into the continents we know. In the deep future, many scientists expect another supercontinent to form, though the exact arrangement is uncertain. It might gather around the equator. It might close the Atlantic. It might form near the pole. Different models produce different names and shapes, but the underlying point is the same. Earth will rearrange itself, and the arrangement of land changes climate. A supercontinent is not just a bigger continent. It changes ocean currents. It changes rainfall. It can create huge interiors far from moisture, where deserts stretch across distances that feel impossible. It can alter coastlines, marine habitats, monsoons, and the global carbon cycle. Mountain belts can rise where plates collide, changing weather patterns and erosion rates. Volcanism can increase in some regions. The biosphere must adapt to a world with different geography. Imagine Earth 250 million years from now. Not the Earth of our maps. The continents have moved into a new configuration. The oceans have been reshaped. The climate has shifted under a sun that is slightly brighter than today. Coastlines that once held modern cities no longer exist as recognizable lines. Mountain ranges that dominate our imagination may be worn down, while new ones stand in places we cannot yet name. The remains of human civilization, if any are still preserved, are buried deep or recycled by erosion, subduction, and time. If humans are gone, the planet will not be silent. Life may continue in forms that would look unfamiliar to us. Evolution does not aim toward human beings. It explores whatever survival allows. Mammals, birds, insects, microbes, plants, fungi, and entirely new lineages may fill ecological spaces left open by change. If a mass extinction happens, recovery may take millions of years. As it has before, new ecosystems may emerge that no person will ever see. If humans remain, they will not be our kind of humans in any ordinary cultural sense. After millions of years, biological evolution, genetic engineering, artificial habitats, space settlement, or technological transformation could make the word human difficult to define. A civilization still connected to Earth after such ages might live underground, underwater, in sealed cities, in orbital structures, or across multiple worlds. Or there may be no civilization at all, only geological traces of one brief species that once lit the night side of the planet. That is the strange scale of Earth's future. The planet can outlast cultures so completely that even our greatest monuments become sediment. Mount Everest is not permanent. The Himalayas are young mountains in geological terms, rising from the collision of India and Eurasia. Given enough time, even the tallest peaks erode. New mountains rise elsewhere. The ocean floor is recycled. Continents are scarred, folded, heated, buried, and exposed. The oldest rocks preserve fragments of Earth's memory, but most surfaces are rewritten. 1 billion years is enough time for almost everything familiar to vanish. And yet the deeper danger for Earth is not an asteroid, a supercontinent, or erosion. It is the sun. The sun feels constant because it has been stable for the entire history of human civilization. Every sunrise arrives with such ordinary confidence that it becomes easy to forget the sun is not a lamp. It is a star. It is aging. And stars do not remain unchanged. At the center of the sun, hydrogen fuses into helium. This fusion releases energy, and that energy moves outward through the sun before escaping as light. Over time, helium accumulates in the core. The core's structure changes. To maintain balance against gravity, the sun slowly becomes more luminous. This process is not dramatic from century to century, but over hundreds of millions of years, it matters. The sun is expected to brighten gradually as it ages on the main sequence. A small increase in solar output can have enormous consequences for Earth, because our planet's climate is balanced delicately between incoming sunlight, reflected sunlight, greenhouse gases, clouds, oceans, ice, and outgoing infrared radiation. Earth is habitable because the balance is right. Change the balance enough, and the same planet begins to behave differently. Long before the Sun becomes a red giant, Earth may stop being comfortable for complex life. This is one of the most important truths about the future of the planet. The end does not wait until the Sun swells into a giant red sphere. The dangerous changes begin much earlier, while the Sun still looks broadly like the Sun. As solar brightness increases, Earth receives more energy. Weathering processes can remove carbon dioxide from the atmosphere over geological time, because warmer temperatures and rainfall can accelerate chemical reactions between rocks and CO2. In a simple sense, Earth has a thermostat. More warmth can increase weathering, which can lower carbon dioxide, which can reduce greenhouse warming. But this thermostat is not perfect, and it has limits. Plants need carbon dioxide for photosynthesis. If atmospheric CO2 falls too low, many plants struggle or die. Different kinds of photosynthesis have different tolerances, but the long-term trend toward lower CO2 under a brighter sun can threaten plant life. If plants decline, food webs change. Animals that depend on plants suffer. Oxygen production changes. Soil systems shift. The biosphere begins to lose complexity. This could happen long before the oceans boil. A future Earth may still have blue water and clouds, but fewer forests. Later, fewer large animals. Later still, only hardy organisms in protected niches. The death of Earth as a rich living world may not begin with fire. It may begin with the slow starvation of photosynthesis. That is more frightening in some ways. A planet can remain physically beautiful while becoming biologically poorer. As the sun continues to brighten, the carbon cycle's ability to protect Earth weakens. More water vapor enters the atmosphere. Water vapor is itself a greenhouse gas. More heat leads to more evaporation, which can lead to more trapping of heat. Under the wrong conditions, this feedback can push a planet toward a moist greenhouse state. In that future, Earth's upper atmosphere contains more water vapor. Ultraviolet light from the sun can break water molecules apart. Hydrogen, being light, can escape into space. Oxygen can react with rocks or remain temporarily in the atmosphere, depending on conditions. Over long periods, Earth begins losing water, not as oceans pouring into space, but as molecules broken apart high above the surface. This is one of the most terrifying versions of planetary death. The ocean does not have to disappear in one boiling event. It can be dismantled, molecule by molecule, year by year, age by age. Eventually, if the warming becomes severe enough, Earth could enter a runaway or near-runaway greenhouse path. Venus is the warning image, though Earth's path and details would not be identical. Venus today is a world where the greenhouse effect became extreme, leaving a surface hot enough to melt lead under crushing atmospheric pressure. It is not simply closer to the Sun. It is a reminder that rocky planets can lose their habitability when climate feedbacks cross dangerous thresholds. Earth has more advantages than Venus did in some respects, including its current distance, oceans, plate tectonics, and biological cycles. But the Sun's slow brightening gives no planet unlimited time. The habitable zone moves outward. Earth stays where it is. This mismatch is the clock beneath every distant sunrise. In perhaps hundreds of millions to more than 1 billion years, depending on the model and assumptions, Earth may become too hot for complex life as we know it. The timeline is uncertain because climate feedbacks are complex, but the direction is clear. A brighter sun means Earth's long-term habitability is temporary. Think about what that means. The dinosaurs never knew they lived under a star that would one day sterilize the planet. Early mammals did not know the sun was slowly setting a deadline. Ancient humans looked at the same star and made calendars, myths, rituals, and navigation systems. Modern science finally revealed that the sun is both the giver of life and the source of Earth's eventual unmaking. Not because it is evil, because it is a star. The first victims of the far future may be the most vulnerable ecosystems: coral reefs, tropical forests, cold-adapted species, shallow seas, mountain habitats. As temperatures and atmospheric chemistry shift over deep time, ecological zones migrate if they can. But migration requires somewhere to go. When the entire planet changes, escape becomes difficult. At first, life retreats. Then, it simplifies. Complex organisms need stable environments, oxygen, food webs, reproductive cycles, and tolerable temperatures. Microbes can survive far more extreme conditions. Earth's biosphere began with microbial life, and it may end with microbial life. The first living things were small, hidden, chemical, and resilient. The last may be the same. This gives Earth's future a strange symmetry. For billions of years, microbes ruled the planet before animals existed. Later, complex life flourished. Forests spread. Fish swam. Insects flew. Reptiles walked. Mammals diversified. Humans appeared and looked back at the entire story. But in the far future, as heat rises and ecosystems collapse, the planet may return to a microbial age. Not because evolution goes backward, because extreme conditions favor simpler survivors. The last living things on Earth might not see sunlight in the way we imagine. They might live underground, in deep rock fractures around remaining water, protected from surface heat. They might use chemical energy rather than sunlight. They might persist after the surface has become too hostile for plants or animals. They might survive in small refuges long after the biosphere above them has become a memory. The future of Earth is not only about death, it is about retreat. Life withdraws from complexity into endurance. And even that endurance has a limit. As the sun brightens further, surface water becomes unstable. Oceans shrink. Salinity changes. Remaining seas become hotter, more isolated, more chemically extreme. The water cycle weakens as surface conditions pass thresholds. Clouds may behave differently. Weather as we know it may fade, then transform into something stranger. The blue planet becomes less blue. Imagine standing on Earth in that distant era. If anything like a person could stand there. The sky might still be bright, but not welcoming. The air might be thick with water vapor and heat. The ground might be dry where oceans once stood. Salt flats could mark the ghosts of seas. The continents, already rearranged by tectonics, would bake under a stronger sun. The moon would still exist, farther away than today, raising weaker tides. The stars would still shine at night, if clouds allowed them to be seen. But the world beneath them would no longer be a home for creatures like us. This is not science fiction in the sense of impossible fantasy. It is the logical consequence of stellar evolution. A planet can be perfectly placed for life for a while, and then the star changes. The tragedy is that Earth is not failing. Earth is following the rules. At this point in the future, humanity, if it still exists, would face choices beyond anything current civilization can meaningfully prepare for. Remaining on Earth's natural surface would become impossible. Survival would require artificial habitats, migration to other worlds, moving Earth's orbit, shading the planet, altering atmospheric chemistry, or living in environments completely separated from the outside climate. Some of these ideas sound absurd today, but 1 billion years is a long time. A civilization that survives for such spans would not be a civilization like ours. It might move planets, build star shades, engineer habitats across the solar system, or leave the inner solar system entirely. It might not use biology in the way we do. It might preserve Earth as a museum, transform it into a managed world, or abandon it when the energy cost becomes unreasonable. The question becomes uncomfortable. Is Earth humanity's permanent home, or only humanity's birthplace? Every creature before us lived and died inside Earth's boundaries. Even birds, whales, and migrating animals remained tied to the planet's systems. Humans are the first species capable of understanding that Earth will not remain habitable forever, and that survival may eventually require leaving. That knowledge is powerful. It is also lonely, because leaving Earth would not be like moving to another country. It would mean accepting that the place where life began, where oceans formed, where the first cells divided, where every ancestor walked, swam, crawled, grew, hunted, hid, loved, and died, is not the final refuge. The future of Earth forces us to separate home from permanence, and the first half of Earth's future ends with this realization. Before the sun becomes a red giant, before Earth is swallowed or scorched, before the final planetary drama begins, the planet may already lose what made it Earth to us. The biosphere may simplify, the oceans may retreat, the climate may pass beyond comfort, the surface may become a place for machines, microbes, or memories. But the sun will not stop there. After billions of years of slowly growing brighter, it will exhaust the hydrogen fuel in its core. The balance inside the star will change. Gravity will compress the core. The outer layers will respond. The sun will begin to leave the long, stable phase that made Earth possible. And when that happens, Earth's future enters a much more violent chapter. But before we follow the sun into that violent chapter, there are other futures hiding inside the calmer one. Some of them happen so slowly that they almost feel gentle. The moon, for example, is moving away from Earth. Not quickly enough for anyone to notice by looking up at night, but measurably. Laser experiments using reflectors left by Apollo astronauts show that the moon drifts outward by a few centimeters each year. That sounds tiny, almost meaningless, until time is allowed to do what time does best. Over millions of years, the moon grows slightly more distant. Its apparent size in the sky becomes a little smaller. Total solar eclipses, those moments when the moon perfectly covers the sun's disk, become rarer and eventually impossible. There will come a time when the moon is too far away to fully cover the sun from Earth's surface. Future observers, if any exist, will still see eclipses, but not the same kind that humans travel across continents to witness today. One of Earth's most beautiful coincidences has an expiration date. The moon also slows Earth's rotation through tidal friction. Today, a day is about 24 hours. In the distant past, days were shorter. In the distant future, they become longer. The change is tiny from year to year, but it matters across deep time. Longer days change the rhythm of sunlight and darkness. They can affect climate patterns, winds, tides, and biological cycles. They remind us that even the basic unit of human life, morning to night, is not absolutely fixed. Earth's future is full of these quiet losses. Not every ending screams. Some endings are simply the last perfect eclipse, the last familiar coastline, the last glacier in a mountain range, the last night when a certain constellation rises over a certain city that no longer exists. Another hidden future is the magnetic field. Earth's magnetic field is generated by motion in the liquid outer core, where molten iron and nickel move through convection and rotation. This magnetic shield helps guide charged particles from the solar wind around the planet. It does not make Earth invincible, but it matters. It protects the atmosphere from some forms of erosion, helps preserve the environment around Earth, and creates the auroras that glow near the poles. The magnetic field is not perfectly stable. It wanders, it weakens and strengthens. Magnetic north moves. Over geological time, the field has reversed many times, with magnetic north and south trading places. These reversals do not happen on a human schedule, and they do not mean the planet suddenly loses all protection forever. But they reveal that Earth's shield is alive in its own strange way, generated by a core that is cooling slowly, moving deeply, and still carrying heat from the planet's formation. In the very distant future, Earth's interior will continue to cool, plate tectonics may eventually slow, volcanic activity may decline, the carbon cycle that helps regulate climate may weaken. The magnetic field depends on internal motion, and while Earth's core will remain active for a very long time, no planetary dynamo is eternal. Mars may be a warning here. Mars once had a more active interior and evidence of an ancient magnetic field, but it lost its global dynamo long ago. Its atmosphere thinned over time, and the surface became cold, dry, and exposed. Earth is larger than Mars and has remained geologically active much longer. Still, its internal heat is finite. Radioactive isotopes decay, primordial heat leaks away. Convection changes. Mantle plumes rise and fade. Subduction carries crust downward. But if the system loses enough vigor, the style of tectonics could change. A future Earth with weaker tectonics would not recycle carbon in the same way. It might have fewer volcanoes replenishing atmospheric gases. It might become less able to regulate climate over geological ages. This is one reason the sun's slow brightening is so dangerous. Earth's long-term habitability depends on two clocks working together, the star above and the planet below. If the star grows brighter while the planet's geological thermostat becomes less flexible, the safe window narrows. The surface environment becomes more dependent on processes that are themselves changing. Habitability is not a single gift. It is a balance between many temporary systems. There is also the future of the oceans as chemical worlds. Today's oceans are not just water. They are reservoirs of heat, carbon, salt, nutrients, dissolved gases, currents, and life. They absorb carbon dioxide from the atmosphere, move energy across the globe, feed clouds, support marine ecosystems, and help regulate climate. But oceans change when the atmosphere changes. More carbon dioxide can make seawater more acidic. Warmer water holds less dissolved oxygen. Stronger stratification can reduce mixing between surface and deep layers. Nutrient cycles can shift. Marine heat waves can stress ecosystems that evolved within narrower temperature ranges. In the near future, these changes matter for coral, plankton, fish, coastal communities, and the human food web. In the far future, they matter for the entire biosphere. If oceans become warmer and more stagnant in some eras, oxygen pore zones can expand. Earth's past includes episodes when parts of the ocean became anoxic, meaning depleted of oxygen. Such conditions can be devastating for marine life. Sometimes they are connected with mass extinctions, volcanic activity, climate change, and disrupted circulation. A future warmer Earth does not need to lose all life to become biologically harsh. It can lose richness. It can lose complexity. It can become dominated by organisms that tolerate heat, low oxygen, high salinity, or chemical extremes. To the human eye, such a world might still be colored by life. Microbial mats can be vivid, algae can bloom, bacteria can paint shorelines and mineral surfaces, but the presence of color is not the same as the presence of a stable, diverse, familiar biosphere. The Earth of the distant future may be alive in ways that would feel alien to us, and that is important. When we say Earth may become uninhabitable, we usually mean uninhabitable for us, for animals like us, for forests like ours, for crops like ours, for cities like ours. Life is wider than humanity. Microbes can survive in boiling springs, acidic pools, dry deserts, frozen brines, buried rock, and dark vents at the bottom of the sea. The last life on Earth may not resemble the life we most love. It may be microscopic, stubborn, and hidden. For a long time, that hidden life could persist. Deep underground, temperatures rise with depth, but there are zones where liquid water, rock chemistry, and microbial metabolism may continue even when the surface becomes punishing. The deep biosphere today already shows that Earth's life is not confined to sunlight. Some organisms live on chemical energy from reactions between water and rock. Some survive in pores, fractures, and sediments far beneath the surface. They live slowly compared with surface organisms, but slow life is still life. In a future when the surface becomes too hot, the underground may become a refuge. Not forever, but longer than forests, cities, or animals. This changes the emotional shape of Earth's ending. The planet does not go from green to dead in a single cinematic cut. It becomes a world of shrinking options. The surface loses comfort. The oceans lose stability. The atmosphere loses balance. Life changes address. It moves into extremes. It becomes smaller, stranger, harder to find. The last chapter of life may be quiet enough that no eye witnesses it. There is another future that belongs specifically to humans, if humans survive long enough to meet it. We may not remain confined to Earth. In the coming centuries, human presence may expand to the Moon, Mars, asteroids, orbital habitats, and perhaps the outer solar system. At first, those places will not be replacements for Earth. They are too harsh, too cold, too airless, too dependent on machines. But the act of building even small settlements beyond Earth changes the meaning of planetary risk. A species that exists in one biosphere is vulnerable to one biosphere's disasters. A species spread across worlds is still vulnerable, but in different ways. If humanity becomes multiplanetary, the future of Earth becomes less identical with the future of humanity. That may sound hopeful. It is also sad, because it means the story can continue while the birthplace declines. Imagine a distant human descendant standing under a dome on Mars, looking toward a bright star in the sky and knowing it is the sun. By then, Earth may be warmer, wetter in the atmosphere, drier at the surface, and harder to visit. The blue planet may become a sacred place, a restricted place, a dangerous place, or a memory from archives. Children born elsewhere might learn about oceans the way we learn about ancient seas that vanished before humans existed. At even greater distances in time, our descendants, if they exist, may have moved farther out. As the sun brightens, Mars could temporarily become more habitable, in some ways, receiving more warmth than before. Icy moons might change. Outer worlds could become more interesting as sunlight increases. But this is not a simple rescue. More sunlight also means changing radiation environments, changing atmospheres, and eventually the chaos of the sun's giant phase. A civilization planning across billions of years would not think only in terms of planets. It would think in terms of orbits, energy, materials, artificial habitats, and stars. Maybe the future home of Earth life is not another planet at all. Maybe it is a swarm of habitats moving through the solar system. Maybe it is sealed oceans inside engineered worlds. Maybe it is generation ships crossing interstellar space. Maybe it is digital minds or biological descendants so altered that they no longer require Earth-like environments. Every answer sounds strange because the time involved is strange. 1 billion years is longer than complex animal life has existed on land. It is long enough for evolution to make old assumptions meaningless. So when we imagine the entire future of Earth, we have to separate several stories that overlap but are not the same. There is the future of the rock. There is the future of the biosphere. There is the future of humanity. There is the future of the sun. These stories interact, but they do not end at exactly the same time. Earth as a planet may survive long after Earth as a living paradise is gone. Life may continue after humans leave or vanish. Humans may continue after Earth becomes hostile. The Sun may transform the entire inner solar system long after the first warning signs appeared. That layered future is more realistic than a single dramatic apocalypse. It is also more disturbing, because it means there is no one moment when everything suddenly becomes simple. There are thresholds. There are retreats. There are decisions. There are losses too slow for one generation to notice and too large for a civilization to ignore. The first threshold is already visible in the near-term climate. The next thresholds belong to ecosystems, oceans, ice, coastlines, and human adaptation. Beyond them lie geological rearrangements, supercontinents, changing circulation, and altered carbon cycles. Farther still waits the brightening sun, the weakening comfort of the habitable zone, the slow collapse of complex life, and the loss of surface water. By the time the sun leaves the main sequence, Earth will already have lived through many endings. The end of today's coastlines, the end of today's ice, the end of today's species distributions, the end of today's continents, the end of today's forests, the end of today's oceans as we understand them. The red giant phase is not the beginning of danger. It is the final announcement. And that is where the second half of the story must go. Because after the long, slow future of climate, geology, biology, and human choice, Earth faces something no adaptation can negotiate with forever. The star that made the planet alive begins to change into something that can no longer leave it untouched. Before that final stellar transformation, it helps to slow the timeline down and watch Earth as if the future were passing beneath us from orbit. In the first centuries, the changes are human scale. Lights shift across continents as populations move. Coastlines are defended in some places and surrendered in others. Farms adapt to new rainfall patterns. Some forests are replanted, some are burned, and some migrate uphill or poleward, one generation at a time. The atmosphere is still breathable, the oceans are still blue, and the moon still hangs above the same world. But the easy assumption of stability has been broken. In the first thousands of years, ruins become part of geology's surface story. Concrete cracks, metals corrode, satellites decay from orbit or become silent debris. Some records survive in cold, dry, protected places. Others vanish because water, heat, life, and human neglect are powerful erasers. A future archaeologist might find plastics in sediments, traces of nuclear materials, altered carbon ratios, and cities reduced to strange mineral layers. Our age may become visible less as monuments and more as chemistry. That is a humbling thought. Civilizations often imagine themselves through their buildings. Planets remember through layers. In tens of thousands of years, Earth's orbit and tilt cycles continue to shape ice ages, if the climate system still allows them in familiar form. Natural cycles known as Milankovitch cycles influence how sunlight is distributed across seasons and latitudes. In the past, these cycles helped pace glacial and interglacial periods. In the future, their effects will interact with whatever atmosphere humanity leaves behind, and whatever slow feedbacks unfold afterward. This means the future is not a simple warming line drawn smoothly across time. Earth can still have regional shifts, abrupt transitions, circulation changes, temporary stabilizations, and delayed responses. Ice sheets can grow or shrink depending on the balance of temperature, snowfall, ocean heat, and atmospheric composition. Deserts can expand, then contract. Forests can return in one era and retreat in another. The climate is not a thermostat dial turned once and left alone. It is a living machine with many gears. That complexity is why predictions become less precise the farther we look. But uncertainty is not the same as ignorance. We know the sun will brighten. We know continents move. We know oceans respond to heat. We know greenhouse gases matter. We know life depends on energy, chemistry, and environment. We know Earth's surface conditions have changed dramatically before. The exact future map may be uncertain, but the fact of change is not. In hundreds of thousands of years, some consequences of today's actions may still echo, yet they will be mixed with natural cycles and new events. Species that survive the next few centuries may evolve into new forms. Human descendants, if present, may guide evolution intentionally or accidentally. Domesticated species might become wild again. Invasive species today could become ordinary parts of future ecosystems. Coral reefs may be replaced in many regions by different communities. Forests may reorganize around heat, fire, drought, and human land use. The living world is not a museum trying to preserve itself. It is a negotiation with conditions. In millions of years, almost no familiar species remain unchanged. Evolution works through variation, selection, isolation, extinction, and opportunity. If humans disappear, other organisms will not pause in respect. They will fill niches, compete, adapt, and transform. Rats, birds, insects, cephalopods, plants, fungi, microbes, or descendants of creatures we barely notice today could become dominant in ecosystems that do not exist yet. There is no guarantee that intelligence like ours appears again. Large brains are expensive. Technology requires not only intelligence, but bodies capable of manipulating the environment, social learning, energy access, stable enough conditions, and many accidents of history. Earth may remain alive for a long time after humans, but never again produce a species that builds telescopes. That possibility is strangely terrifying. Not because life would fail, because awareness might. The universe may be full of living worlds that never develop minds capable of understanding stars. Earth may have done something rare when it produced a species that could trace its own future into deep time. If that awareness disappears, the planet continues, but the knowing part of the story ends. Of course, humanity may not disappear. It may change instead. A future intelligent lineage could preserve memory across geological time. It could mark dangerous asteroids, manage climate, move genetic libraries, restore ecosystems, mine the moon, redirect comets, or build habitats beyond Earth. It could become careful in ways our early industrial civilization was not. It could also become reckless in new ways, creating risks we cannot easily imagine. The future is not automatically noble just because it is advanced. Power increases consequences. A civilization with the ability to alter planets can save biospheres or damage them at larger scale. A civilization able to move asteroids can protect Earth or turn orbital mechanics into a weapon. A civilization able to engineer life can restore lost species or create fragile dependencies. The farther the future goes, the more Earth's fate may depend not only on natural forces, but on what intelligence decides to become. This is where Earth's future becomes more than astronomy. It becomes a moral problem stretched across time. If we know Earth is temporary as a habitat, what do we owe the future? If the planet will one day become hostile no matter what we do, does that make present life less important? Or more? If every coastline, forest, language, and species is temporary, should that make us careless, or should it make the temporary things more precious? Science can tell us the sun will brighten. It cannot decide what beauty means before the brightening takes it away. Science can describe sea level rise. It cannot by itself choose which city is worth defending, which community receives help, or how much suffering is acceptable. Science can model a future supercontinent. It cannot tell a civilization how to carry memory through the collapse of its own maps. That is why the entire future of Earth is terrifying in a deeper way than simple destruction. It asks whether a species can act wisely while standing between the shortness of its own life and the vastness of planetary time. Most of the future will not be lived by us, but some of it will be shaped by us. Then the timeline moves onward. 10 million years, 50 million, 100 million. The familiar world becomes increasingly historical. The continents are recognizably related to ours at first, then less so. Ocean gateways open and close. A seaway can change global circulation. A mountain range can pull moisture from winds and create rain shadows. A volcanic province can release gases that disturb climate. Erosion can expose rocks that draw carbon dioxide from the air. Biology responds, then changes the conditions it responds to. Earth is not a passive stage with life walking across it. Life and planet co-write each other. Plants changed weathering. Microbes changed atmosphere. Oxygen transformed surface chemistry. Shell-building organisms altered carbon cycles. Humans changed land, air, and ocean in a geological instant. Future life, whatever form it takes, will keep interacting with rock, air, water, and sunlight until the external energy balance grows too harsh. By 200 million years from now, the night sky will also be different. Stars move. The Sun orbits the center of the Milky Way roughly every couple hundred million years. Constellations are temporary patterns created by our viewpoint and the current positions of nearby stars. The shapes we know as Orion, Scorpius, Cassiopeia, and the Big Dipper will distort and dissolve over time. Some stars will die. Others will drift into new alignments. The Milky Way itself will continue its long approach toward Andromeda, though the major merger lies billions of years ahead. A future observer on Earth would not see our sky. They would see another sky over another map, under a brighter sun. That single sentence contains almost the entire future of the planet. Same world, different everything. By the time the next supercontinent forms, Earth may be hotter not only because of geography and greenhouse effects, but because the sun's luminosity has increased. The interior of a huge landmass can become brutally dry, especially far from ocean moisture. Seasonal extremes can intensify. If the supercontinent sits in certain latitudes, it could create vast desert belts. If it forms differently, the climate might be less severe in some areas, but no arrangement cancels the solar clock. The future supercontinent is not guaranteed to kill mammals or end complex life by itself, but it could stress ecosystems severely, especially combined with a brighter sun. That combination is important. Earth's dangers do not line up politely one at a time. They stack. A hotter sun changes the baseline. A new supercontinent changes atmospheric circulation. Volcanism can change gas levels. Evolution changes which organisms are present to respond. A future biosphere faces the sum of these forces. This is why the far future cannot be treated like one forecast. It is more like a set of overlapping stories, each written at a different speed. Human decisions act over decades and centuries. Ice sheets respond over centuries to millennia. Species evolve over thousands to millions of years. Continents move over tens to hundreds of millions. The sun ages across billions. Earth's future is terrifying because all of those clocks are running at once. And the slowest clock is the one nobody can stop. When the sun finally begins to leave its stable middle age, every earlier chapter becomes a prelude. The changed coastlines, the lost species, the supercontinents, the longer days, the fading eclipses, the altered oceans, the possible human migrations, the retreat of life into refuges. All of it happens under a star that was quietly preparing its own transformation. For billions of years, the sun gave Earth time. In the next part of the story, it begins taking that time back. That is the point where Earth stops being only a planet with a changing environment and becomes a planet waiting beneath a changing star. The difference matters. Climate can be managed for a while. Coastlines can be defended for a while. Species can be protected, moved, stored, or restored for a while. Continents cannot be stopped, but civilizations can learn to live around their motion if they last long enough. Even impacts can sometimes be deflected if they are found early. But stellar evolution is not an emergency response problem. It is the background law behind the entire story. No war can hold back a brighter sun. No treaty can make hydrogen return to the solar core. No civilization can ask the star to remain young because one small planet still needs it. If intelligence survives long enough to face that era, it will need to think beyond adaptation and toward departure, transformation, or engineering on a scale almost impossible for us to picture. So the first half of Earth's future leaves us here, at the edge between the slow and the immense. Behind us are the futures that still feel connected to the world we know. Warming oceans, moving coastlines, changing ecosystems, drifting continents, weakening old maps, longer days, rarer eclipses, and life forced to adjust again and again. Ahead is the future in which the sun itself becomes the main character. Not as the familiar yellow disk above farms, cities, deserts, forests, and seas, but as an aging star whose next stages will decide whether Earth is scorched, stripped, swallowed, or left behind as a dead remnant of the living world it once carried. And that is where the second half begins. It begins not with a sudden disaster, but with a slightly brighter morning. At first, no one in the distant future would notice it from one day to the next. The sun would not change color overnight. It would not swell across the sky in a single terrifying season. It would not announce that Earth had entered the final chapter of its habitable life. The change would be quiet, measured over millions of years, hidden inside the ordinary rhythm of daylight. But the sun is not a lamp that stays the same forever. It is a star, and every star is a machine that slowly changes as it burns its fuel. Deep in the core, hydrogen is fused into helium. Helium builds up where hydrogen used to be. The balance inside the sun adjusts. The core contracts slightly, the outer layers respond, and over immense spans of time the sun grows brighter. That small word, brighter, is where the danger begins. A brighter sun does not need to explode to change Earth. It only needs to give the planet a little more energy than the climate system can safely release back into space. For a while, Earth can compensate. Weather patterns shift, clouds change, oceans store heat. Carbon moves between air, water, life, and rock. The planet has survived many climate swings before, from ice ages to greenhouse periods, from asteroid impacts to volcanic winters. But the future sun is not a temporary event. It is not a volcano that erupts and then quiets. It is not an asteroid strike that leaves one scar. It is not a human industrial age that might be corrected by technology, restraint, or recovery. It is a permanent upward pressure from the star at the center of the solar system. Century after century, age after age, the basic energy balance becomes harder to maintain. Long before the sun becomes a red giant, Earth begins to lose the comfort that made it familiar. The first great danger is not that the surface bursts into flame. It is that water becomes harder to keep in the right place. Oceans are not just blue decoration on a planet. They are climate engines. They absorb heat, move it around the globe, feed storms, dissolve carbon dioxide, carry nutrients, and provide the medium in which life began. As the sun brightens, evaporation strengthens. More water vapor enters the atmosphere, and water vapor is itself a greenhouse gas. That creates a feedback. More heat evaporates more water. More water vapor traps more heat. More trapped heat evaporates still more water. The process does not have to be instant to be devastating. The planet can remain recognizable for a long time, while slowly moving toward a state from which ordinary recovery becomes impossible. Imagine a future Earth where the oceans still exist, but they no longer feel like the same oceans. Tropical zones spread farther. Heat waves become more severe. Wet regions may grow violently stormy, while dry regions become harsher. The atmosphere carries more moisture, and storms can release it with more force. The planet still has continents, clouds, rain, and seasons, yet the old climate boundaries begin to lose meaning. Then the deeper change begins. Carbon dioxide slowly disappears from the air. That sounds strange, because in our own age, carbon dioxide is known mostly as a warming gas. But over geological time, Earth has a thermostat that works through rocks. Rainwater reacts with carbon dioxide, forming weak acids that weather silicate minerals. Rivers carry the products into the ocean. Eventually, carbon is locked away in carbonate rocks and sediments. Volcanoes return some CO2 to the atmosphere. For billions of years, this slow cycle has helped regulate climate. As the sun brightens, the thermostat pushes in one direction. Warmer temperatures speed up weathering. Faster weathering pulls more carbon dioxide out of the air. At first, that may help cool the planet. But life, especially plants, also needs carbon dioxide. A world can become too warm and too carbon poor at the same time. That is one of the crueler parts of Earth's future. The biosphere does not necessarily end, because there is too much of one problem. It can be squeezed between several problems at once. Heat rises, carbon dioxide falls, rainfall patterns change, oceans become stressed, nutrients shift, habitats move faster than many organisms can follow. The planet becomes less like a stable home and more like a system trying to preserve balance with fewer and fewer tools. Plants would be among the first great casualties in the deep future. Different plants use different chemical pathways. Some can handle lower carbon dioxide better than others. Some are built for heat and drought. Some can survive where others fail. But as carbon dioxide continues to fall and temperatures continue to climb, photosynthesis becomes harder across the planet. Forests retreat. Grasslands change. Food webs lose their base. Animals do not need the oceans to boil before their world becomes impossible. They only need the green foundation beneath them to fail. A future Earth without forests is not just a sad image. It is a planet losing one of its major biological engines. Forests move water from soil to air. They make clouds more likely. They shelter millions of species. They store carbon, anchor soils, and shape weather around them. When large plant communities vanish, the air, land, and oceans all respond. The world becomes simpler in the worst possible way. Complex animals would decline next. Not all at once, not everywhere. Evolution is resourceful, and life has survived impossible-looking bottlenecks before. There may be refuges. High latitudes could remain tolerable longer. Mountains might hold cooler zones. Deep oceans could stay protected for a time. Underground environments might continue almost untouched while the surface changes beyond recognition. But complex life depends on networks, food chains, oxygen cycles, ecosystems, and stable niches. When the networks fail, the most demanding organisms disappear first. Earth's future is not one clean extinction event. It is more like the shrinking of a stage. At first, the stage is the whole planet. Then, it becomes the cooler parts of continents and oceans. Then, it becomes special refuges. Then, it becomes hidden cracks, deep aquifers, geothermal systems, caves, and oceanic leftovers. The story of life narrows from a world of forests, reefs, insects, birds, mammals, and flowering plants to a planet where survival belongs mostly to organisms that need little, grow slowly, and can tolerate extremes. The last life on Earth may not look dramatic. It may not have eyes. It may not move in a way we would notice. It may not know daylight. It may live under rock, in salty pockets, in deep crustal fractures, or in warm chemical environments, powered by reactions rather than sunlight. Long after the last tree has fallen and the last animal has disappeared, microbes may continue in places where the surface has already become hostile. That is one of the strangest possibilities. Earth could be biologically alive while looking dead from orbit. A spacecraft passing by might see a dry, hot planet with no blue oceans, no green continents, and no obvious biosphere. Yet beneath the crust, tiny communities might still be using chemical energy, exchanging molecules in darkness, holding on to the last inheritance of the ancient oceans. Life began small, and it may end small. The oceans are the next great threshold. As the sun keeps brightening, evaporation intensifies beyond anything Earth can safely balance. Water vapor reaches higher into the atmosphere. In the upper atmosphere, ultraviolet light from the sun can break water molecules apart. Hydrogen, being light, can escape into space. Oxygen may react with surface materials or remain temporarily in the atmosphere. But the key fact is simple. Once hydrogen escapes, the water is gone. This is how a planet can lose its oceans without needing them to be scooped away. The water rises as vapor. Sunlight breaks it apart, and space slowly steals the lightest pieces. Over enormous time, the loss becomes irreversible. The oceans that shaped every coastline, carried every ship, fed every storm, and reflected every moonrise begin to leave the planet atom by atom. There is something almost quiet about that image. No single wave marks the end. No final tide explains itself. The ocean does not vanish in one night. It thins through climate, atmosphere, chemistry, and escape. Lakes shrink. Inland seas become salt flats. Coastlines retreat beyond maps. The deep basins become shallower, warmer, saltier, and finally empty. What remains is not simply dry land, but the exposed floor of a vanished world ocean, crossed by mineral deposits and the ghosts of currents that will never flow again. The atmosphere changes with the water. Clouds lose their familiar cycle. Rain becomes rare, then impossible. Weather becomes dust, heat, wind, and chemistry instead of living water. Without oceans to moderate temperature, the surface swings into harsher conditions. Rocks that once sat under kilometers of water face the sky. Sediments dry, crack, and bake. Former coral reefs become stone ridges on a Dead Sea floor. The planet still rotates, still orbits, still has a moon, still receives sunlight, but it no longer behaves like Earth. It becomes something else. Not exactly Venus, because every planet has its own path. Not exactly Mars, because Earth is larger, warmer, and chemically different. It becomes a future version of itself, a post-ocean Earth, a planet that once carried life but no longer has the surface conditions that made complex life possible. And the sun has still not reached its most dangerous phase. This is important. By the time Earth's oceans are gone, the sun may still look broadly like the sun. Brighter, yes. More dangerous, yes. But not yet the huge red object people imagine when they think of the end of the solar system. That means Earth's living world is likely to end long before the famous red giant stage. The death of habitability comes before the most spectacular destruction. The final future of Earth is not only about the sun becoming enormous, it is about the long betrayal of normal sunlight. For most of Earth's history, sunlight was the gift that powered life. It warmed the surface. It drove photosynthesis. It evaporated water so rain could fall. It made climate, weather, food, and oxygen possible. In the far future, the same source becomes too much. The same star that allowed life to exist slowly pushes the planet outside the range where life can remain abundant. A world can die from the thing that once kept it alive. After the oceans are lost and the biosphere has retreated or vanished, Earth enters a long period as a dry, hot, increasingly altered planet. The continents may still move for a time if the interior remains active. Volcanoes may still erupt. The moon may still raise tides in whatever atmosphere or crustal response remains. Meteors may still burn overhead if an atmosphere is left to catch them. But the story is now geological, not biological. The planet becomes a record rather than a home. Every mountain range, every old seabed, every fossil layer, every buried city of traces of civilization remain, becomes part of an archive that no living surface ecosystem can read. The history of Earth might still be written in stone, but the readers may be gone. If any descendants of humanity or another intelligence survive elsewhere, Earth would become a relic world, visited perhaps as one visits a ruin. And then the sun changes more dramatically. Eventually, the hydrogen in the sun's core is no longer enough to maintain the old balance. The core has become rich in helium. Fusion in the central region changes. The structure of the star reorganizes. Hydrogen continues burning in a shell around the core. The outer layers expand. The surface cools in temperature even as the total light output increases. The star begins its transformation into a red giant. From Earth, if Earth still has a surface from which anything could watch, the sky would become unrecognizable. The sun would no longer be a small, bright disk. It would grow larger, redder, and more overwhelming. It would stain the sky with a dull, swollen light. Shadows would soften and stretch. The idea of noon would change. The horizon would glow before the star rose fully. The old sun, the one small enough to hide behind a hand, would be gone. The red giant phase is not simply bigger sunlight. It is the sun losing the quiet stability that defined most of its main sequence life. Its outer layers become extended and thin compared with the star we know, but the scale is enormous. The star loses mass through powerful stellar winds. Its luminosity rises. The inner solar system becomes a place of heat, drag, changing orbits, and uncertainty. Mercury is almost certainly doomed. The small, innermost planet has spent billions of years scorched by sunlight, airless and cratered. But the red giant sun would turn its orbit into a death sentence. As the sun expands, Mercury lies too close to survive. It would be engulfed or destroyed, its rocky body falling into the outer layers of the star or being stripped apart by heat and drag. The first planet becomes one of the first offerings to the dying sun. Venus follows the same general fate. Venus already shows us what a runaway greenhouse can do to a rocky world, with crushing pressure, hot surface temperatures, and a thick atmosphere. But even Venus is not prepared for the red giant sun. Its orbit sits deep in the danger zone. The expanding star and rising luminosity would remove any remaining distinction between planet and victim. Venus, the planet once sometimes called Earth's twin, would be swallowed or destroyed in the sun's expanded envelope. Then comes the question that matters most to us. What happens to Earth? The answer is not as simple as people often imagine. One version says Earth is swallowed. The sun expands enough that Earth's orbit lies inside the outer atmosphere of the red giant. If that happens, Earth does not survive as a planet in any meaningful sense. It encounters stellar material. Friction and drag steal orbital energy. The planet spirals inward. Its surface melts, vaporizes, and dissolves into the star that once warmed it. The planet that carried oceans, life, continents, storms, civilizations, and memory becomes material inside the aging sun. Another version allows Earth to avoid direct engulfment. As the sun loses mass through stellar winds, its gravitational hold weakens. Planetary orbits can expand outward. Earth may drift farther away as the sun sheds part of itself into space, That orbital expansion could help Earth avoid being physically swallowed. But avoiding engulfment is not the same as surviving in any hopeful sense. By then, Earth would already be sterile, scorched, oceanless, and unrecognizable. A dead planet can survive a close call and still be dead. This uncertainty is one reason the future is so unsettling. We do not know whether Earth's final form is swallowed matter or a burned remnant orbiting a white dwarf. The details depend on stellar evolution, solar mass loss, tidal interactions, and how the sun's outer layers behave when they expand. The difference is enormous for Earth as an object. It matters very little for Earth as a living world. Life is gone either way. Still, the physical ending matters. If Earth is engulfed, the story ends inside the sun. The surface would not merely become hot, it would lose the conditions that define a planet's surface. Rock vaporizes. Atmosphere merges with stellar gas. The orbit decays. The crust and mantle are torn, heated, mixed, and destroyed. Earth becomes an ingredient in the last active stages of its star. If Earth survives outside the expanded sun, it becomes a different kind of ghost. It may be stripped, melted, and resurfaced. Its remaining atmosphere could be lost. Its crust might be transformed by extreme heat. Any old features that survived earlier ages could be erased. It would circle a changing star from a widened orbit, no longer blue, no longer green, no longer alive. It would be a blackened or baked relic carrying only mass, chemistry, and perhaps deep internal traces of what it used to be. The Moon's future is tied to this fate. For billions of years, the Moon has slowly drifted away from Earth, pulled outward through tidal interactions while Earth's rotation slows. In the deep future, this dance continues, but the red giant sun changes the stage. If Earth is engulfed, the Earth-Moon system cannot continue in its old form. The Moon may be pulled, heated, destabilized, or separated depending on the details of the encounter. If Earth survives, the Moon may survive too, but it would no longer shine over oceans, forests, or living nights. A moon over a dead Earth is one of the loneliest images in astronomy. No tides in living seas, no eclipses watched by animals, no human eyes following its phases. The same cratered face would still turn toward Earth, but Earth would no longer be the world that made moonlight meaningful. The relationship could persist physically while losing every living witness that ever gave it beauty. Beyond Earth, the outer solar system also changes. Mars, already cold and thin-aired in our age, would receive far more sunlight during the sun's red giant stage. For a time, people sometimes imagine Mars becoming more habitable as the sun brightens. There is some truth in the basic idea that the habitable zone moves outward. Worlds that were frozen can warm, ice can sublimate, outer moons can change, but the details are harsh. A brighter sun does not simply make Mars into a second Earth. Mars lacks a thick atmosphere, active surface water, and the same geologic protections. It may warm, but warmth alone is not habitability. The icy moons of Jupiter and Saturn could also feel the change. Europa, Ganymede, Callisto, Enceladus, Titan, and other distant worlds are frozen largely because sunlight is weak where they orbit. As the sun becomes brighter, those worlds receive more energy. Ices can soften or evaporate. Atmospheres can form temporarily or be stripped. Subsurface oceans may change. Some places might briefly become more chemically active. Others might lose the frozen shields that protected their interiors. There may be a future moment when the best chance for surface liquid water moves outward. Not to Earth, but to regions that are now too cold. That idea sounds almost comforting until we remember the timescales. The sun's red giant phases are not calm, steady, multi-billion-year havens like Earth's main sequence era. They are unstable, changing, and brief compared with the long age of life on Earth. A moon or distant world might enjoy a temporary thaw. But temporary is the key word. Habitability is not only about temperature. It requires stability, chemistry, atmosphere, protection, and time. A warmed moon in a dying solar system is not a second beginning. It is a brief window opened inside a collapsing house. Meanwhile, the sun continues shedding mass. The outer layers loosen. Stellar winds carry gas outward into space. The star that once held itself in a tight, golden sphere becomes larger, cooler on the surface, brighter overall, and less gravitationally commanding as it loses material. The solar system reacts. Orbits expand. Small bodies in distant reservoirs may be disturbed. Some comets may be nudged inward. Some objects may drift away more easily. The solar system becomes less tightly bound. The sun is still the center, but it is no longer the same anchor. The architecture built over billions of years begins to adjust to a star losing its own outer body. Planets that survive move in altered paths. Asteroids and comets respond to changing gravitational conditions. Dust, gas, and debris spread through the system. The familiar map of planets around a stable yellow star gives way to a dynamic aftermath. Then, the sun reaches stages that are difficult to imagine calmly. After its red giant expansion, after helium burning and later shell burning phases, the sun enters a period when it sheds its outer layers more completely. It will not explode as a supernova because it does not have enough mass. That is important. The sun's death is not the violent death of a massive star. It is not a blast that forges huge amounts of heavy elements and leaves behind a neutron star or black hole. The sun dies in a quieter but still immense way. It releases its outer atmosphere into space. Those layers drift outward, illuminated by the hot, exposed core. From far away, the result could look like a planetary nebula, a glowing shell, ring, or complex cloud of gas expanding into the surrounding space. The name is misleading. It has nothing to do with planets, except that early astronomers saw some of these nebulae as small round disks through old telescopes. In reality, they are the cast-off envelopes of dying stars. For the solar system, this is the sun exhaling its last visible beauty. The material that once helped make sunlight is released into space. Gas spreads outward, glowing for a time under ultraviolet radiation from the hot core. If Earth has survived as an object, it would orbit under a sky no living creature could see, while the remains of its star form a luminous structure around the center of the system. The scene could be beautiful from a safe distance. Up close, it is the aftermath of the death of the star that made Earth possible. At the center remains a white dwarf. This is the sun's core, exposed and compressed into an object roughly Earth-sized, but containing a large fraction of the sun's mass. It no longer produces energy through steady fusion like the sun does today. It shines because it is hot, because it is cooling from a violent transformation. It is a stellar ember, dense, bright at first, slowly fading over timescales far longer than human history. A white dwarf sun would change the solar system completely. There would be no warm habitable zone where Earth used to be. No familiar yellow daylight. No gentle, stable sunlight like the main sequence era. Any surviving planets would orbit a small, dense remnant. The central object might be brilliant but tiny, a point of harsh light, rather than a broad warming disk. Over time it would cool, dim, and redden, moving gradually toward darkness. If Earth survived, its orbit would be wider than before, because the sun would have lost mass. The planet would receive far less energy from the white dwarf than it once did from the sun. But this would not be a return to safety. It would be a dead world, circling a dead star, too late for oceans, air, forests, animals, or civilizations that remained tied to the surface. The solar system after the Sun becomes a white dwarf is not empty. The giant planets may remain. Jupiter, Saturn, Uranus, and Neptune could continue orbiting, though their paths may have expanded. Their moons may remain, altered by lost sunlight and changed tides. Asteroids and comets may still move through the dark. Dust from disrupted bodies could fall toward the white dwarf. Some distant objects may become unstable over immense periods and be scattered inward or outward. Even dead systems can remain active in quiet ways. Astronomers have observed white dwarfs polluted with heavy elements, meaning they contain traces of rocky material in their atmospheres. Since heavy elements should sink quickly inside a white dwarf, those traces suggest that asteroids, comets, or planetary debris can fall into dead stars long after the main star has died. A future white dwarf sun might also receive fragments from what remains of its planetary system. The solar system's debris could continue telling the story of planets even after the planets themselves are altered or gone. This gives Earth's future another possible ending. If Earth is destroyed, pieces of it may not simply vanish. Some material could become part of the Sun during engulfment. Some could be ejected. Some could join debris fields. Some could eventually fall onto the white dwarf or be scattered into the wider galaxy. The atoms of Earth have already traveled through previous generations of stars before becoming our planet. In the far future, they may travel again. The planet's identity ends before its matter does. That distinction matters. Earth is not only rock, it is arrangement. It is ocean above crust, air above ocean, life inside chemistry, memory inside life, and history inside layers. The atoms can survive while the world is gone. Carbon, oxygen, iron, silicon, and water-derived hydrogen can be moved, mixed, stripped, or swallowed. But the Earth we mean when we say Earth is the living structure that those atoms form together. That structure has a time limit. There is also a quieter transformation happening in the sky itself. As the Sun grows, the meaning of distance changes. In the present solar system, Earth is close enough to receive gentle daylight. Mars is cold. Jupiter is distant. And the outer planets live in a dim region where sunlight is only a weak echo of what Earth receives. During the Sun's old age, that arrangement shifts. The inner worlds are burned or swallowed, while distant places receive levels of sunlight that once belonged much closer to the star. The asteroid belt would not remain untouched. Many asteroids are dry rock and metal, but others hold hydrated minerals, ice, carbon-rich material, and chemical records from the solar system's youth. A brighter aging sun would warm them differently. Ice trapped in their interiors could sublimate. Surfaces could crack. Dust could be released. Orbits could change as the sun loses mass and as thermal forces act on small bodies over long times. The asteroid belt may become more active, not because it comes alive, but because the quiet, cold storage of the inner solar system begins to fail. Some fragments may be pushed into new paths. A changing sun means changing gravity. The loss of solar mass makes every orbit respond. The effect on large planets may be slow and orderly, but smaller bodies are easier to disturb. Resonances shift. Asteroids that once stayed in stable regions may be nudged out. Comets from farther reservoirs may be loosened. The dying solar system could experience new waves of impacts and scattering long after Earth's living age is over. For a dead Earth, impacts would no longer be biological disasters. There would be no forests to burn, no animals to flee, no oceans to throw tsunamis across the globe. But impacts would still reshape the surface. They would dig into old crust, expose buried layers, melt rock, and erase parts of the planet's archive. A future crater on a dead Earth would not end a world. It would add one more scar to a world already ended. The atmosphere, if any remains, would be strange. The air we know depends on life as much as geology. Oxygen is not simply a background gas that planets naturally keep. It was built by photosynthesis and maintained by living systems over immense time. Once complex photosynthesis collapses and surface life ends, oxygen will not necessarily remain in its familiar abundance forever. It can react with rocks, escape, or be altered by the hot chemistry of a changing planet. Nitrogen, carbon compounds, sulfur compounds, and vaporized minerals may all play roles in whatever atmosphere remains during the scorching eras. A planet can keep an atmosphere and still be unlivable. Venus proves that. Titan proves it in another way. Mars proves the opposite problem, where the atmosphere is too thin to protect or warm the surface well. Earth's future atmosphere may pass through several hostile forms: humid and greenhouse-heavy, then oxygen-poor and carbon-poor, then dry and heated, then stripped, expanded, or partly lost during the sun's giant phases. None of these stages resemble the air that lungs evolved to use. The magnetic field may also change with time. Earth's magnetic field is generated by motions in its liquid outer core. It protects the planet from some charged particles and helps shape the way solar wind interacts with the atmosphere. Over geological time, the field reverses, wanders, strengthens, and weakens. In the far future, as Earth's interior cools and the mantle changes, the dynamo may not last forever. If the magnetic shield weakens significantly, before or during the most intense solar stages, atmospheric loss and radiation exposure could become even harsher. But by then, the surface may already be beyond biology. That is a repeating pattern in Earth's far future, but not a repeated sentence. Many dangers arrive after the living world has already lost the ability to care. Radiation, impacts, atmospheric stripping, orbital changes, and crustal transformation may continue for ages, but their meaning changes once there is no biosphere left to damage. They become geological events on a silent planet. Mars may become briefly interesting in a different way. As the sun brightens, the cold planet warms. Frozen CO2 and water ice may respond. Subsurface ice could become more mobile. The polar caps and buried deposits might release gases or vapor. The sky could thicken slightly for a time, depending on how much volatile material remains available. But Mars is not simply waiting to become Earth. It is smaller, drier, less geologically active, and has lost much of the atmosphere that could have supported a stable, warm climate. If future explorers or descendants of Earth ever tried to use Mars as a refuge, timing would matter. Too early, and Mars is cold, dry, irradiated, and difficult. Too late, and the sun's evolution becomes unstable or temporary. There may be a window when Mars receives more comfortable energy than it does now. But a window is not a permanent home. It would be another station along the outward retreat from a brightening star. The moons of Jupiter offer deeper possibilities. Europa's hidden ocean, Ganymede's internal layers, and Callisto's ancient ice-rich crust all exist in a region that today is far from comfortable sunlight. Internal heat, tidal effects, and subsurface water make them scientifically fascinating even now. In the far future, stronger sunlight could alter their surfaces dramatically. Ice that once protected oceans may thin, shift, or sublime. Surface chemistry may accelerate. Radiation from Jupiter would still be a danger, but the thermal environment would no longer be as frozen. This does not guarantee life would bloom there. Life is not automatic when ice melts. Chemistry must be right. Energy must flow in usable ways. Environments must remain stable long enough for biology to begin or persist. A temporarily warmed Europa might be more active, but if the change is too fast or too violent, it could harm any hidden biosphere rather than help it. Habitability is not the same as warmth. It is the right kind of warmth in the right environment for the right amount of time. Saturn's system may become even stranger. Titan today is a world of methane lakes, thick nitrogen atmosphere, organic chemistry, and extreme cold. Under a brighter sun, methane would not behave the same way forever. Lakes could evaporate. Atmospheric chemistry could shift. Water ice on the surface might soften under later conditions. And for a temporary era, Titan could become a world where different kinds of liquids and chemistry move through changing climates. It would not become Earth, but it might become one of the most transformed places in the future solar system. Enceladus, with its bright icy surface and subsurface ocean, could also change. The plumes that make it so fascinating today are powered from within, not by sunlight alone. But extrasolar energy would still affect the surface, the ice, and the environment around the moon. A warmer outer solar system might reveal things currently hidden, or erase delicate clues before anyone can read them. In the long future, the same brightening that kills Earth may briefly expose secrets in the frozen worlds. The Kuiper Belt waits even farther out. Pluto, Charon, Arrokoth, and countless icy bodies live in deep cold today. They preserve primitive materials from the early solar system in a freezer of distance. When the sun becomes a red giant, even these distant regions receive more warmth than they do now. Some ices may become active. Thin temporary atmospheres may form around small worlds. Surfaces that have been quiet for billions of years could vent, crack, haze, or darken. For a while, the solar system's frontier could wake up, not with cities or forests, but with sublimating ice, escaping gas, and chemical changes on worlds that spent most of solar history almost asleep. The inner solar system would be dying, while the outer solar system might be stirring. That contrast is one of the most haunting parts of stellar evolution. A star's old age can kill one region, while briefly energizing another. But the awakening does not last. After the sun sheds its outer layers and becomes a white dwarf, the extra warmth fades. The outer worlds cool again. Temporary atmospheres collapse. Activity slows. Volatile materials refreeze if they have not escaped. The solar system enters a long age of cold around a small remnant star. Any brief outward migration of habitability ends, and the great darkness returns. This means the future solar system may have multiple endings, depending on where you stand. On Earth, the ending is heat. On Mars, it may be a failed opportunity. On Europa or Enceladus, it may be a dangerous thaw. On Titan, it may be the loss of a strange methane world before water ever has a stable chance. In the Kuiper Belt, it may be a short awakening, followed by a longer freeze. The sun does not destroy every place in the same way. It rearranges the entire meaning of distance. That is why the phrase "future of Earth" eventually becomes too small. Earth is the emotional center of the story, but the real event is solar system evolution. Every planet, moon, asteroid, comet, and distant ice body responds to the changing star. The death of Earth's habitability is one chapter in the broader aging of the sun's empire. And somewhere in that changing empire, if life or intelligence has spread, the old home planet may become a destination of memory. Future beings might return to Earth not to live, but to study. They might orbit above dry basins where oceans once moved. They might search for fossil coastlines, buried cities, ancient sediments, or the chemical signature of vanished life. They might preserve samples of rock, the way we preserve meteorites now. Earth could become the sacred ruin of biology, the place where a spreading lineage began. But if no one remains to visit, the planet's archive stays closed. The rocks still hold the story. The story simply has no reader. That possibility is as frightening as the heat. A world can be filled with evidence and still be silent. A dead Earth could contain proof of oceans, oxygen, forests, animals, machines, and minds, while drifting under a sky with no witness. The universe does not require memory in order to continue. It can preserve traces for a while, then erase them through heat, impacts, erosion, burial, melting, or stellar transformation. Without observers, even the most meaningful history becomes physical pattern. That is why the survival of memory may become as important as the survival of bodies. If humanity or its descendants ever face the deep future, they may not be able to save Earth as a living planet, but they might save records, genomes, languages, art, maps, fossils, seeds, and the story of what Earth was. They might carry oceans in data, forests in DNA, and human voices in archives moving through space. A civilization leaving Earth would not only be escaping danger, it would be deciding what parts of a world can be carried when the world itself cannot. For humanity, or for any intelligence that might descend from Earth, the future raises an uncomfortable question. Do we try to save Earth, leave Earth, or accept that planets are temporary homes? Saving Earth sounds natural. It is our origin. It is the only living world we know. But saving a planet from stellar evolution is not like repairing a climate, deflecting an asteroid, or building seawalls. The brightness of the sun is not a local problem. The red giant phase is not a disaster that lasts a few years. It is the evolution of the star itself. Any civilization facing the deep future would need options far beyond ours. One option is migration. Life could move outward through the solar system as the habitable zone shifts. Habitats could orbit Mars, the asteroid belt, Jupiter's moons, Saturn's moons, or artificial stations designed to receive the right amount of energy from the changing sun. If civilization survives millions or billions of years, it may not remain on one planet. It may become distributed among worlds, habitats, and eventually other star systems. Another option is planetary engineering. In theory, a civilization could try to shade Earth from extra sunlight using enormous structures in space. A giant sunshade near a gravitational balance point could reduce the energy reaching the planet. Over shorter timescales, such ideas belong to speculative climate engineering. Over billion-year timescales, they become part of the question of whether Earth's habitable era could be extended. But as the sun brightens more and more, shading becomes harder. A sunshade that works for one era may not work for the next. The required scale increases. Maintenance must continue across geological time. Impacts, orbital drift, material fatigue, and political or biological continuity become enormous problems. Technology can be powerful, but deep time is relentless. Even a very advanced civilization must keep functioning longer than most species exist. A more extreme idea is moving Earth. Some speculative concepts imagine using repeated gravitational encounters with asteroids or comets to slowly transfer orbital energy and move Earth outward. In principle, if Earth could be moved farther from the sun, as the sun brightens, it might remain in a more comfortable zone for longer. In practice, the engineering is almost beyond comprehension. A small error could destabilize the moon, the climate, or the planet's orbit. The process would require precision maintained over millions of years. And even if it worked, the red giant phase would still loom. To keep Earth alive all the way through the sun's transformation, the planet would need to be moved enormously far outward or protected by technologies that dwarf anything we can build. At some point, preserving Earth as a natural living world becomes less realistic than preserving life somewhere else. That may be the hardest truth for a planet-loving species. The goal may not be to keep Earth forever. The goal may be to carry Earth's life beyond Earth. Not because Earth failed, but because no planet around a changing star can be permanent. Earth has already given life more than 4 billion years. It has carried oceans, microbes, forests, animals, minds, and the ability to understand its own future. That is not a small achievement. It is an extraordinary temporary success. A temporary home can still be precious. The far future also changes how we think about extinction. In ordinary time, extinction is tragedy measured against survival. A species disappears while the world continues. But in deep time, the planet's habitability itself ends. Eventually, there is no ecosystem left to preserve on the surface, no climate left to restore, no forest waiting to regrow. The stage is dismantled. The question becomes whether life has expanded beyond the stage before the lights go out. This is why space exploration matters in a deeper way than adventure. It is not only about flags, footprints, rockets, or curiosity. It is about whether intelligence can become more than a local accident on one temporary planet. If life remains only on Earth, then Earth's future is life's future. If life spreads, then Earth becomes the beginning rather than the boundary. But spreading is not simple. Mars is harsh. The Moon is airless. Asteroids are small and exposed. The outer solar system is cold. Interstellar travel is slow beyond anything human societies are built to imagine. Generation ships, artificial habitats, frozen embryos, digital archives, seed banks, and self-replicating probes all enter the conversation. But none are easy answers. They are attempts to solve a problem set by time itself. The sun gives us billions of years, but not forever. That is generous by human standards and terrifying by cosmic standards. 1 billion years is longer than all recorded history, multiplied beyond recognition. It is longer than the rise and fall of countless species. It is long enough for continents to rearrange, oceans to change shape, mountains to rise and vanish, and evolution to produce forms of life that would look alien to us. Yet compared with stars, galaxies, and the future of the universe, it is a passing era. Earth exists inside that contradiction. It feels ancient, but it is temporary. It feels stable, but it is changing. It feels like the center of life, but it is one planet in orbit around a star that is aging whether anyone watches or not. The future of Earth is terrifying, partly because it removes the comforting idea of permanence. The mountains are not permanent. The oceans are not permanent. The continents are not permanent. The atmosphere is not permanent. The moon's position is not permanent. The sun's kindness is not permanent. Even the meaning of a sunrise changes if you follow the story far enough. But terror is not the only feeling the future gives. There is also perspective. The future makes the present more extraordinary. Right now, Earth still has oceans that move under moonlight. It has air thick enough to breathe. It has temperatures that allow water to fall as rain and freeze as snow. It has forests, plankton, insects, birds, fungi, bacteria, coral, deserts, ice sheets, rivers, and cities. It has minds capable of imagining a time when all of this will be gone. That ability is strange. A planet has produced beings that can look at their star and understand that the star will change. Matter arranged itself into life. Life arranged itself into intelligence, and intelligence learned enough physics to predict the end of the world that made it. That does not stop the ending, but it means the ending is not entirely hidden. We know the future because the universe leaves clues. We study other stars at different ages. We observe red giants, planetary nebulae, and white dwarfs. We watch stellar evolution written across the sky in millions of examples. The sun's future is not guessed from myth. It is inferred from physics and from the lives of stars around us. Every dying star is a preview. Every white dwarf is a warning. Every glowing nebula is a remnant of something that once shone more steadily. The sky is filled with examples of what the sun will become. Some are beautiful, some are violent, some are quiet. But all of them remind us that stars are not eternal fixtures. They are processes. They form, burn, change, shed, collapse, cool, and fade. Earth's future is tied to one such process, close enough that we call it day. In the end, the entire future of Earth can be told as a movement through dependence. First, Earth depends on the sun for warmth. Then, it suffers because the sun gives too much. Then, it is transformed because the sun grows unstable. Then, it is ended, preserved, or abandoned because the sun becomes something else. That is the arc behind all the details. Climate change, continents, supercontinents, disappearing eclipses, dying ecosystems, evaporating oceans, red giant expansion, planetary survival, white dwarf cooling. These are not separate stories. They are chapters in one long transition from a living planet around a stable star to a relic world in a changed solar system. If Earth is swallowed, the final image is fire without witness. The planet enters the sun's expanded outer layers. Its surface is erased. Its orbit decays. Its materials join the star. There is no Earth afterward. Only atoms that once were Earth moving inside or around the dying sun. If Earth survives, the final image is quieter. A dead, burned planet orbits a white dwarf in a wider, colder solar system. The oceans are gone. The air is gone or transformed. The continents no longer matter. The moon, if still present, circles a corpse world. The sun is no longer the sun as life knew it, but a dense cooling ember. The planet remains, but the world is finished. Neither ending is gentle. One destroys Earth physically, the other preserves the body after the life has left it. And yet, both endings are still far away. That distance matters. The terrifying future is real, but it is not immediate. It does not excuse carelessness now, and it does not make present choices meaningless. If anything, it does the opposite. A temporary world is not worthless because it is temporary. A song is not worthless because it ends. A life is not worthless because it is finite. The value is in what happens while the conditions exist. Earth's future is enormous, but the present is still ours. We live in the narrow, bright interval between formation and ruin, between molten beginning and stellar ending, between the first oceans and the last dry basin. We are not at the beginning of the story. We are not at the end. We are somewhere in the middle of the only living world we know, aware enough to see both backward and forward. That awareness should make the planet feel less ordinary. Every cloud is temporary. Every coastline is temporary. Every forest is temporary. Every night sky is temporary. Even Earth itself, as a living world, is temporary. But temporary does not mean insignificant. It means rare in time. It means the conditions that feel normal to us are actually a brief arrangement in a solar system that will eventually become unrecognizable. It means this era of blue oceans and breathable air is not the default state of matter, but a delicate outcome that has lasted long enough for creatures to notice it. The entire future of Earth is terrifying because it shows that no home is guaranteed forever. But it is also humbling because it shows what Earth has already done. It survived impacts, magma oceans, ice ages, oxygen revolutions, mass extinctions, shifting continents, changing atmospheres, and a brightening star. It turned rock and water into cells, cells into ecosystems, ecosystems into minds, and minds into a question about what happens next. That question does not save the planet by itself, but it changes the kind of universe the planet lives in. For most worlds, the future arrives without anyone understanding it. For Earth, at least for now, the future has been seen. Not perfectly, not completely, but clearly enough to know the shape of the path. The planet will change. Life will struggle. The oceans will not last forever. The sun will grow old. the inner solar system will be transformed. Earth will either be swallowed or left behind. The white dwarf will cool. The old home of life will pass into darkness, memory, or matter scattered through space. And long before that final era arrives, every generation that ever lives here will inherit the same truth. We are living on a world with an ending. Not a mythic ending, not a sudden cinematic ending, a real astrophysical ending written into the life cycle of the star above us. That is why the future of Earth is not just a timeline. It is a mirror. It shows us how fragile habitability is, how powerful stars are, how temporary oceans can be, and how rare this present moment may be. It shows us that the planet beneath our feet is not an eternal platform, but a moving, changing world inside a much larger cosmic process. And the most terrifying part is not only that Earth will end, it is that, for a while, it does not. For a while, it remains warm enough, wet enough, stable enough, and alive enough for something like us to exist. For a while, sunrise still means morning instead of warning. For a while, the ocean still returns the sky. For a while, the moon still pulls tides across living shores. For a while, Earth is still Earth. That is the part of the future that matters most, because the ending is already written in the star. But the meaning of the time before it is not. And that is where this future becomes more than a prediction. It becomes a responsibility placed inside a narrow era of sunlight. We cannot stop the sun from aging, and we cannot make Earth permanent by wanting it to be permanent. But we can understand the planet more carefully while it is still alive. We can protect the systems that still work. We can learn from the worlds around us. We can build knowledge that may outlast any single coastline, nation, language, or machine. The far future does not ask us to panic. It asks us to notice that oceans are rare, to notice that air is not guaranteed, to notice that stable sunlight is a temporary gift, to notice that Earth is not just a place beneath us, but a phase in the life of a planet, moving around a changing star. One day, the sun will no longer be gentle. One day, the seas will be gone. One day, the continents will no longer matter to anything alive. One day, the planet that gave birth to every human story may become a relic, a memory or material inside the star that once made it bloom. But not yet. For now, Earth is still blue. For now, rain still falls. For now, the night side still glows with cities, lightning, auroras, and moonlit clouds. For now, the future is terrifying because the present is still beautiful enough to lose. And that may be the real reason this story matters.